All right, so I've got a ton of announcements to make because this is an unusual week, but I'm going to wait on the announcements until everybody's finished with the quiz. So we'll dive in and then we'll come back and talk announcements when we're all ready. Yeah, you can work on it after class if you want to. Sure. Okay, so on page 18, I'm just going to highlight there are these three integrals that we're going to try to find. Integral from 1 to infinity of 1 over e to the x plus 1. There's another integral with an infinity, and a third integral with an infinity. And you had an integral with an infinity on it on this quiz that we're finishing up right now. And the way you find it, I don't think I'm giving away anything here, is to find an antiderivative and then deal with the infinity, right? But it hinges on being able to find an antiderivative. And I don't know about you, but I have no earthly idea how to find an antiderivative of 1 over e to the x plus 1. It seems so simple, but I don't have any technique. Likewise, I don't know how to find an antiderivative of that, and I don't know how to find an antiderivative of that. So I'm 0 for 3 on those integrals. I can't find a single antiderivative here. So the tool that we're going to use today to handle these, well, first we'll say this. The goal, when I say, here it says determine convergence or divergence, the goal is not necessarily to say that, oh yeah, this converges and it's 2.3. That's the final answer. The goal is not to figure out what it's equal to. The goal is either this is finite or this is infinite. Those are the only two choices, and that's all the information we're after. Is there finite area under that curve, or is there infinite area? No longer are we hoping to actually get a final number, like maybe on the quiz, you have a final number. So the thing that we're going to use here is this new tool called the comparison test. And what we're going to do is compare each of these integrals to some integrals that we already know whether they're finite or infinite. And so that's where we start today. And I'll put this out there at the outset of today. The technique that we're going to follow to figure out whether this thing is infinite or finite, I don't really know where it goes. It doesn't go anyplace for me after this. We'll use the comparison test a little bit down the road when we talk about this thing called series. It's not the most compelling test. I don't have any applications I can give you that says, hey, this is why the comparison test is super useful. I'll say that it's going to allow us to determine whether something's finite or infinite, which we couldn't do for any of these three without something called the comparison test. And it's also going to give us a sense or give us an opportunity to become a little more mathematically mature. You know, you want to get better at writing, you have to write harder and harder material. You want to get better at writing mathematics, you have to write harder and harder mathematical material. So we're going to have a sense to really prove some things, like mathematically prove some things, and get a little bit stronger at writing mathematics. But I don't have any nice applications that'll say at the end of the day, okay, and now here's the cool thing we can do with this new tool. So just putting that out there. So let's come back to page 17. 17 starts with this list of three, what they're called useful integrals for comparison. That's what your book calls them, 3 useful integrals for comparison. And the first one, I'll just write an example of the first one. Integral of 1 over x squared, integral of 1, actually we'll do the ones that you guys did last time. You don't need to write this, but you can if you want. 1 over x to the 0.9. On the group activity at the end of last class, which is way back on Wednesday because we lost the snow day, but the group activity that you guys did had these two integrals here, right? 1 over x to the 1.1 and 1 over x to the 0.9, between 1 and infinity. Can you go back and see? What you figured out whether these converged or diverged. So go back and check. What does the first one do? This one right here converged. You guys proved that by finding an antiderivative, dealing with the infinity, and it turned out you actually got some finite answer when all was said and done. And how about the other one? This one diverged because you got infinity when you dealt with the infinity. There was infinite area underneath that curve based on what you did last class. And so what you figured out was actually there's like a magical cutoff that determines the convergence, the convergent ones from the divergent ones. Where's the cutoff? Is at 1. When that power is 1, it diverged. And if the power was less than 1, like there, it also diverged. But anything bigger than 1, like that guy, and it converged. That was one of your big conclusions from last class. So that's exactly what this first line here says. It says the integral any positive number up to infinity. It doesn't matter what number is down there. It's the infinite part that's going to be important. This 1 over x to the p, it converged if p was bigger than 1, like 1.1, and it diverged if p was less than or equal to 1, like 0.9. All right? This is what you guys proved last time, or you collected evidence that would indicate that's true. And then you looked at the same integrals, but instead of going from 1 to infinity, you went from 0 up to, maybe it was 1, I don't remember exactly. What's the problem with this integral? That's right. If you try plugging 0 in, you get something undefined. So the problem here isn't that we're going to infinity, it's that we've got this infinite discontinuity at 0. And so you ended up doing the same exact integrals, and you came up with here a different conclusion. Anybody know which one of these was the convergent one? You can go back and check. I know not all groups maybe got up to this one. Yeah, this one, the left-hand one, actually was the bad side. The left one diverged. And this guy over here, I call it bad for divergent, but that's just my editorializing, I guess. And so in this case, the good side of 1, the power is 1, is the other side now. And so that guy right there, this integral from 0 to any positive number, 0 is the undefined part, it converged if p is less than 1. So you can see how the roles have kind of swapped, and diverges if p is bigger than or equal to 1. And then there's this last one that we haven't seen yet together, but hopefully we'll buy it. As long as there's an e downstairs, there's a really big number down there, right? E to a big number is huge. And so if I take 1 and divide it by this huge number, what kind of numbers do I get? Very small, very close to 0. So this guy right here converges as long as there are some e's down there. So it feels like it should just converge all the time for any a. Okay, yes, if a is positive, then this e term is really downstairs. But what if a was a negative number, like 1 over e to the negative 2x? Where is that e really? That e is really upstairs, right? And so now I've got huge amounts of area. I'm not even approaching the x-axis anymore. So as long as the e is really downstairs, then this integral right here will converge. And a bigger than 0 is our way of making sure the e is really downstairs. So if a is more than 0, that integral converges, otherwise diverges. So 3 useful integrals for comparison. I'm going to call these things, or call this list UIC, useful integrals for comparison, okay? So we're going to come back and use these things. So let's see if we can build this comparison test, this theorem. So let's take a look at this picture. And it says here, suppose that 0 is less than or equal to f of x is less than or equal to g of x for x sufficiently large. So some function is always bigger than another one. Which is the bigger function in this picture? X to the negative 2 or x to the negative 3? X to the negative 2. So that one, do you guys buy that x to the negative 2 is always bigger than x to the negative 3? Okay, so I don't know what's going on for the negative x's. Where do they change roles? Which one's on top in this picture? Is it x equals 1 actually? Because out here the purple one is on top, but over here the blue one is on top of the purple one, right? Okay, so as long as you're past x equals 1, if you're anywhere out here, then the purple one is above. Fine. Suppose that I tell you that the integral of the purple one, when I go from 1 to infinity, suppose I tell you that integral converges. What that means is that the area starting at 1 and then going out to infinity, everything under the purple is what kind of a thing? Is it finite or is it infinite? Finite, okay? So suppose it's finite. Now take a look at the blue curve, which is the one on the bottom, it's the lower one. What would you say about the area of the blue curve? It must be finite. Do you buy that? If you know that all this yellow stuff is finite, and then you decide that you want to ask yourself about, well, what about the area that's underneath the lower one? Well, if all of the yellow is finite, and the blue is, or this lower one is always lower, then that must be more finite. Doesn't make sense, but it's a smaller finite number, right? Again, the goal is either to decide that the area is finite or infinite. Those are the only two choices. You got to pick the right answer. So if you have something big that happens to be finite, then anything smaller must be finite. And I think that that's what we're going for here in number 3. Suppose you know that the integral of g of x converges. Is g the smaller or bigger? G is the bigger one. What can we conclude? We can conclude that the integral of f of x also converges. Yes, Jody. Mm-hmm. Mm-hmm. So if a is equal to 0, then this is really the integral of some number up to infinity of what? If a is 0, of 1, right? Just plain 1. What does the graph of y equals 1 look like? Just a horizontal line. I want to know where 1 is in my picture here. So how much area is under there if you go forever? Infinite, right? It doesn't even have a chance of coming down. Yeah. Okay. All right. Yeah, end behavior is all we're after, and we're going to use that today. The second thing you said is definitely true. The first thing, surprisingly, is not true. Yeah, so what we saw last time, actually, this 1 over x to the 0.9, this one right here, that curve looks an awful lot like both of the curves that are drawn here. And yet somehow the area under that curve is actually infinite. It's not enough to just say the curve gets close to the x-axis. It could get close to the x-axis fast enough to be a finite area, but if it doesn't get close to the x-axis fast enough, it can still be infinity. It's a very finicky thing, whether it's finite or infinite. Yeah. Yes, please. Thank you. Okay. All right. It's also important not to read too much into the thing we just said. We said if the area under purple is finite, then the area under the blue is finite. Yes? Okay. What if I told you the area under the blue is finite? What does that tell you about the area under the purple? Nothing. If I tell you the area under the blue is finite, the area under the purple could also be finite, but it could be infinity. So we got to make sure we don't read too much into the theorem. But there is another side to this theorem. Suppose that I tell you that the area under the blue was, what kind of a thing would be useful to us? Yeah, if that blue guy diverges, in other words, if the area under the blue is infinity, then how much is the area under the purple is also infinity. It's a little big, it's a bigger infinity, but it's infinity, right? Infinity plus 1. So that is useful to us. So if the integral of f of x, remember f is the one that's underneath, f is the lower one. If f diverges, then what can we conclude? We can conclude that g also diverges. This is page 17. So these two statements together are this thing that we're calling the comparison test. If the big one converges, then so does the little one. If the little one diverges, then so does the big one. I'm hoping that it's reasonable and it's not just like symbols and formulas to memorize. I'm hoping that we buy it. So let's see how we can use it on the next page. We'll take a look at our 3 examples here in number 5. We have to have it be above all the time. We're absolutely assuming that, Jeremy, and we need it. Let's come, why can't I go back? There we go. So the first thing that needs to happen is this right here. We need the one function to always be above the other function. Yeah. Okay, so let's take a look at 5. Determine convergence or divergence. And again, we're not trying to figure out what anything converges to. The answer I'm after isn't the first integral converges to 5.3, it's the first integral converges or the first integral diverges. Those are the two possible answers. Okay, again, 1 over e to the x plus 1. I have no idea how to find an antiderivative of that. But I do know that I buy what Iris said earlier, and that's that the end behavior is going to be important. Which piece of this fraction should make little difference when x is very big, which it will eventually be? The plus 1, right? We buy that the plus 1 is just like decorative. It really has no impact, right? Because e to the x is so huge. Yeah. So how about we say that, what are we saying here? That if x is large, then e to the x plus 1 is basically the same as e to the x. Okay, fair enough. So then how about we ignore the plus 1 for the moment? So we're going to look at the integral of 1 over e to the x, ignoring the plus 1. Okay, in order to figure out if this integral converges or diverges, normally you would have to do an antiderivative, and the limit is b goes to infinity like you did on the quiz. But this should look familiar. This is in our list of useful integrals. Go back to the previous page and find it. Yeah, this is 1 over e to the x. The way the formats work in the book, it keeps it on the bottom. So yes, you could write it as e to the negative x, but I'll leave it this way because we're looking at the thing in the book. So does this converge or diverge? Converges. How much is the a in this one? It's 1. Okay, everybody see it? It's that third line in this list of useful integrals. So I will say that this integral right here converges by the list of useful integrals. I don't know what C is. Useful integrals. What do we call it? I forgot the acronym we came up with. We're on page 17 is the page with the useful integrals. What do we call it? Useful integrals for comparison. That's it. Okay, useful integrals for comparison. And then just to really show that I know what I'm talking about, I'm going to write down what A is. How much is the A in this example? It's positive 1, which is more than 0. That's what the useful integrals tells you. If you have an a that's bigger than 0, converges. So a equals 1, which is more than 0. Yeah. Okay. So that's super. The other thing we need to do is figure out how the two functions compare. I'm trying to compare this function to this function. I already know that the bottom one converges, which means that the area under that curve in the bottom one is finite, right? Are you hoping that the top function is bigger or smaller than the bottom function? One vote for smaller. Well, you're looking at what it is. I want to know what we're hoping for. Are we hoping that the top one will be bigger or smaller than the bottom, given that the bottom is finite? I want the top one to be smaller. Because if the top one is smaller, then it's smaller than something finite, it will be finite, right? It's that picture that we looked at on the previous page. I really want that top one to be smaller. I don't have any control over whether it is or isn't, but that's what I'm hoping for. So let's see if we can compare. So here's what we're going to do. E to the x plus 1 compares to e to the x with what kind of a symbol? Greater than or less than? Greater than. Easy, right? Add 1. Okay, so that's bigger. But what I wanted was what on top of each of these? I wanted 1s on top of each of these, so let's put 1 on top of each of them. And yeah, and what happens to the inequality when you put 1 over? It flips. Is that something we're familiar with? Just as a quick aside, 4 is definitely greater than 3, yes? So 1 over 4 is what? It is less, right? So it works every time you flip over, it changes the direction of that inequality. Okay, and I think we win. That's what we were hoping for. We have a couple of things working together now. we know that the integrand we're interested in is smaller than this integrand. And this guy right here converges. So you have something that's smaller than this other finite thing. So it is a finite thing itself. So we'll just write down our sentence, our concluding sentence. So I'll abbreviate comparison test CT. By the comparison test, and then I'm going to copy the original integral. And then our final conclusion, convergent or divergent? Convergent. Now we're going to do two more examples just like this one. So you'll start to see the pattern in terms of how things are written, but I'll at least pull out some of the details of this pattern right now. As I grade your work, I'm going to be expecting you to be able to write mathematically true arguments like this one. And this might be one of the more complex things that I'm asking you to write so far. So I'm looking for three distinct pieces. One, you gotta find an integral that you know the behavior of. So this 1 over e to the x, we knew it converged from that useful integrals list. Two is this piece right here, where you compare the thing you are interested in, the original, with the thing that you know something about, right? We have to make sure that we've got this inequality, and it's got to be in the correct direction. And then three is the conclusion. So all three of these examples here, you're going to see those same three steps listed out. And like I said at the beginning, it's not the most exciting game to play, but we're going to play it for today. Let's take a look at part B. Integral 1 to infinity, x squared over x to the fourth plus 4x plus 1 dx. I have no idea how to find an antiderivative. I'd be surprised if a simple antiderivative existed. Maybe it does. I don't know how to find it, so let's ignore the stuff that we don't care about. On the bottom, what doesn't matter if x is large? Yeah, not just the plus one, but the 4x is also insignificant. That's a little bit surprising to some folks, but if x is 1,000,000, some big thing, how much is 4x? 4 million, that's pretty significant. But x to the fourth is 1,000,000 to the fourth, which is a 1 followed by 24 zeros? I think it's 24 zeros. Yes. Which dwarfs the 4 million that we were talking about before. So this stuff here makes little difference when x is big. And this agrees with what you saw in pre-calculus, right? You'd ignore everything except for the leading terms. Yeah? Okay, so let's ignore everything except those leading terms. What am I going to do? So we're not going to have space for all three of these here, so I'm going to do the last one on another page. Okay, so what we're going to do is ignore everything except the leading terms. So I've got x squared over x to the fourth, which is also known as 1 over x squared. And 1 over x squared inside of an integral is something I know a little bit about. So I'm going to throw integral signs in front of each of these. And that last integral is in the list. Go to the previous page and find it. The list tells you that it converges or diverges. You just have to identify. What does it do? Converges. This is in the first or second row of the list. It's the first row of the list. You can tell because it's got the infinity there. The second row in the list has a 0. So one of them has 0, one has infinity. So this one right here, we will say converges by this useful integrals for comparison list. And then I'll be really clear. The important letter is on the previous page. Yeah, just go back one page. It's these three facts right here. In row number 1, the letter is not A. What's the letter? It's P. How much is P in this integral? It's 2. What is the cutoff number? Is 1, and 2 is greater than 1. Yeah, and you'd never think that would be worth writing down, but here it's our way of saying, look, I understand exactly what that useful integral thing says. It says if the power is more than 1, the thing converges. So that's our way of writing it. Yeah, Tony.
You said, I'm just going to write this so that I know what it means. But now this is part of what you want, right?
I think I would really like us to write that. Yeah, just the part in the parentheses is the only thing you're asking about. I think I would like us to write that just to be really clear. And you can have the useful integrals list in front of you, so you'll know. You don't have to memorize, oh, it's called A and then it's called P. Like, you'll have it in front of you. But I would like us to really be clear as to what you're looking at in that useful integrals list. Okay, so that's step 1. Step 2 is the integral. So let's think about comparing the two integrands. So let's do this. How does x to the 4th plus 4x plus 1 compare to x to the 4th? It's greater, yes, because you're adding plenty of stuff. So it's greater. So now what are we going to do with both of these? Maybe we'll put a 1 over, and then we'll put an x squared over. So I'm going to put a 1 over right now. And when you put a 1 over, what happens to that inequality? It flips, so it becomes less. And then finally, we're almost at the original integrand. What did I want upstairs? I want x squared, so how about we multiply both sides by x squared? So x squared over and then x squared over x to the 4th. How do these compare? Still less, because you're multiplying both sides by a positive number, right? The same number on both sides, and it's positive. Yeah, no, I don't mind. Yeah, in fact, I'm going to say, I guess this is essentially the only thing I'm looking for. The other things are building it, and if you can build it faster, then that's okay. Yeah. Okay, and what can I say? I can also say this is the same as the 1 over x squared. That's tying it to this red integral that we looked at, right? 1 over x squared, we know something about that. Okay, and then I think we're good. We just have to figure out if this is the right direction. Is this the direction we were hoping for? What did we decide about this integral right here? It converges. That was from our useful list. Here's the direction of the inequality. The thing we're interested in is smaller than the convergent thing. Is that good? Yes. Smaller than some finite number. It must also be finite. So we'll just write our sentence up here. So by the comparison test, and then we'll copy the whole integral. And then slap on the word converges or diverges. What does it do? It converges. Any questions on that one? Go ahead. Absolutely. Yeah. Yeah, you can use these acronyms. Before I wrote the UIC this morning, I wouldn't have had any idea what that meant, but now I understand what it means. So like if you go to some other math teacher, hey, you know how the UIC says if A is bigger than 0, it converges? They won't have any idea what you're talking about. Okay, So we've got one more to do, and I want to do it, but I also want to make sure we talk about all these announcements. So if you're still taking the quiz, I'm going to ask you to pause on the quiz and then start it up again after I finish all these announcements. So, and if you miss any of the announcements, I'm recording this. I'll post it on YouTube, including the announcements. So first thing, there is an under-celebrated holiday coming up this Thursday. What is it? It's Pi Day. Yeah, Lincoln is celebrated quite a bit, but Pi Day doesn't get enough attention. Pi Day, pi the symbol, the number, 314, right? 3.14. 3.1415 to 2015. That will be a day to remember. So Josh shared with me this scan of a restaurant tip. So that was good. Thank you, Josh. All right. I will say celebrate responsibly. All right. First thing here. Okay. So GCC spring break is coming up this next week. However, the buildings are open and the offices are functioning, and the financial aid office in particular is available to help you fill out your FAFSA form. That's the National Financial Aid Form. So if you want help filling this form out, come in on Monday, 1 week from today. Drop in anytime between 9 and 3 in East 144. Write it down if you want to make sure that you know where to go, and they will help you fill out your FAFSA form. It takes about 15 minutes to do a renewal and about 30 minutes to do a first-time form, but apparently it's quite complicated, and they are there to help you. The priority deadline is May 1st, so it's in the future, but this is a great opportunity to get some help on that form. They are also available Tuesday next week for drop-in hours, but it's not here. It's at the Hadley branch of the UMass Credit Union. So if that's helpful to you. Topher. Good. Bring all the tax info. Oh.
Last year I got a bonus from my military, and they counted that as $10,000 a year. I had approved it. I'm like, that's a one-time thing. So they're like, oh, well, you guys make 60 grand. It's like, like 20 grand less than that.
Right. Yeah. All right. So bring lots of tax info with you. I'm sure if you search FAFSA online, you'll find the documents that you'll need to bring with you, but they are there to help. Any other questions or comments on this? Good. Next thing, our calendar has been reprinted. There are copies on the tables, but they might not be distributed quite right. Everybody raise your hand if you don't have a copy of the calendar on your table. I have one here. Who's still missing? Does everybody have the calendar? Okay, so everything has been pushed back again with our third snow day on Friday. So, so everything got pushed down a day, which means that the project number 4 is now due this coming Friday. Project 5 will be assigned Friday, and lots of stuff. So here is what is going on. This week is quite unusual because I will not be here the rest of the week. So you should have a half sheet of paper on your tables. Grab one of those. And again, they're probably not evenly distributed. So who's missing? I have one here. Who needs? Take this one back here. Who else needs? Do you have one? No, you got one? Anybody else? Got extra there. Okay, everybody's got it? Great, let's go through it. So I will be away Wednesday and Friday of this week. I had given you an opportunity to weigh in on whether you preferred I make a YouTube video for those classes or find a substitute. Overwhelmingly, you folks were in favor of the YouTube video. So Jeremy had asked, can you come to when I record? I was going to just be in an empty room and record the 2 lesson plans. So absolutely you can come. It is going to be tomorrow at 2 o'clock in North 403, which is right next door. So if you are free and interested in coming, you should come. Bring your packet. We'll just have Wednesday and Friday's class tomorrow at 2 next door. They're going to be a little bit shorter. Yeah, they'll be a little bit shorter. Okay. All right, if you can't come, then you're going to watch the YouTube video, and you have two choices. You can either watch it on your own time at home or here or at the library or someplace, or, and I think this is my recommendation to you, you come here at 10:40 on Friday and Wednesday, and you watch the thing projected here on the smartboard, and you pause the video when I say pause the video, and then you'll fill in the packet, and you will work with each other. I really think that it can function. I'm starting to feel like my role is not that important as soon as I make the video, but I feel like it can function really well. You guys know each other and you work together. I think it would be super if people could come in at 10:40 on Wednesday and Friday. Okay, so so that's one option. If you are searching for the titles, note that they will be dated according to when they should happen. They're not going to have tomorrow's dates on them, but you have the titles there in front of you. All right, there are then 3 homework assignments that I'm going to ask you to turn in after spring break. I don't want you to turn anything in when I'm out. So the homework assignment from tonight, the one from Wednesday night, and the one from Friday night. You hold on to all of them and you give them to me Monday when we come back from spring break. Okay, next thing, project number 4, this is the one about the gamma function, is due this coming Friday. I'm asking you to slide it under my door by the start of Friday's class. If you get it to me at the end of Friday's class, that's okay. If you're working here at this time on Friday with each other, fine. Right? I think that's a good use of time to work on this project together. That said, if you turn it in late, like after class, I'm going to ask you to write down the date and time when you slid it under there. Questions 5 and 8 on the project are particularly challenging. The very first thing I'm going to do in the video I make tomorrow is provide a hint for question 5 and question 8, all right? For project 4, right, for the gamma function. So, so certainly check that out before Friday if you're looking for a push. I will provide a push tomorrow first thing, okay? All right, that is project 4. Quiz number 4 is scheduled for Monday, March 25th. It's not this coming week, but I'm just putting it out there that the very first thing that's going to happen when you come back from spring break is a welcome back quiz, okay? Just putting it out there. That's first thing. So you can show up 10 minutes early. I'm going to be away for some of it, but I will be checking email. Yeah. Arkansas. What's in Arkansas? Let's see here. Okay. Last announcement here. Project number 5 is assigned Friday, but I'm not going to be here, so I'm assigning it now. It's there on your table. You don't need to look at it before Friday, but let's make sure everybody has one of these. Raise your hand if you don't have project 5. Anybody else? Everybody has project 5? You have one? Yes? Okay. Project 5 is going to rely on you doing something to 4 pieces of chocolate. I'm going to give them to you today. Don't eat the chocolate. You need the chocolate to do the project.
After the project?
After the project, you can eat the chocolate. Right, so make sure you have 4 pieces of chocolate before you leave today, okay? Yeah, but then you have to give me the, yeah. All right. Any questions? I know that this is awkward. There's a lot of stuff. I apologize. I don't like to miss class. I thank you for giving me the opportunity to go and not be here. But I understand that there's a lot of stuff. Any questions on any of this? Okay. Yes. It's I don't have a name for it, but but over the next 2 classes that I'll be YouTubing, we will develop techniques for finding the volume of that shape, whatever it is. Yeah. I mean, it's not assigned, so you can't. I'm not expecting you can do it yet, but it's assigned Friday. It's handed out, but it's assigned. Yeah. By Friday's class, we'll have seen the material. Okay. All right, one last announcement. Peer tutoring here at GCC is very much available, and according to one of the people in charge, is being underutilized this semester. So He said that you could pretty much go there just about any morning and just walk in, and there'll be a tutor available to help you in a number of different subjects. So take advantage of that. Also, peer tutoring is available over spring break, so that might be a nice time to either catch up on some classes or get ahead in some classes. Don't just drop in. It's got to be an appointment over spring break, okay? So you can make an appointment and meet with somebody or several people over spring break. There are. Yeah, absolutely.
I went on this morning classes and asked them questions about how well, yeah, drink substitution. And like I said, they're like, yeah, we'll just change this to you and then so it didn't work.
It might be a hit or miss thing. It might be hit or miss. Okay, we have like 2 minutes. We can speed through this last one, just the highlights here. That integral is part C. Again, I don't know how to find an antiderivative, so I'm stuck there. I'm going to compare it to another integral by ignoring what? Ignore that -1. If x is big, subtracting 1 will make little difference. So at its heart, this is really 1 over the cube root of x squared. Yes? Which is 1 over x to the, oops. Yeah, keep it down there. X to the 2/3. It is, but I'm going to keep it downstairs since we're using this useful list. So I'll stick some integrals in front. And then look again at that list of useful integrals. Here the power is 2/3. Does that converge or diverge? Diverges by the UIC, where the power in this case is what number? 2/3. And how does that compare to the magical cutoff? It is less than. Okay. So there's our first part. And then we're going to build our inequality next. So we were going to compare the cube root of x squared to the cube root, put the -1 there, and then we'll compare that to the cube root of x squared. So that's comparing the thing I started with to the thing I know about. What symbol goes in between? Less or greater? Less than. Yes, definitely less than. You subtracted 1. Super. So what am I going to put on top of both of those? 1 on top. And that changes the direction, which is a good thing for us because we've already decided that the red integral, is it finite or infinite? Infinite. This integral, is it more or less? It's more. The one we're interested in is more than the one we know about. That's the correct direction. It's more than something infinite. It must be infinite. So by the comparison test, original integral, what was it? 1 over cube root x squared minus 1. What does it do? It diverges. Bigger than something that's already infinite. Sorry for going over today. And I think that's about it.